Hello, complex class. I wanted to go ahead and knock out lecture 5 with you, online lecture 5. And like I indicated last time, there's not going to be many more, maybe one more after this one, at most 2. All right, so same setup as before. We're going to work with a function, and we're going to assume that we have an isolated singularity at z0. And when you know you have an isolated singularity at z0, then you know that you have a Lorentz series representation on the deleted neighborhood of z0, some deleted neighborhood of z0, so I'm not going to specify r here. There's just some positive real number r where on that deleted disk, let's draw a little picture. Here's z0, and if you remove z0 and you look at that little disk of radius r, then you have a Lorentz series representation. And so we're going to assume that our representation looks like this. I've gone ahead and used the combined notation where we're just having the CNs here. You've got C0, C1, C2, C3, C4 for the positive powers of Z, the non-negative powers of Z. And then, of course, C minus 1 goes with Z minus Z0 to the minus 1, so on and so forth. It may be convenient to break it up. And when we break it up, just to remind you, we usually think about it as the constant when the power of z minus z0 is 0. I put that over on this side. So I've got a0, a1, a2, a3 goes with the positive powers of z, and then my b's go with the negative power of z. Either way, I'll want to be able to switch back and forth. Okay, so just a comment for you. This part, the sum of the negative powers of z minus z0, this is called the principal part of f at z0. And it turns out that there's 3 cases for the principal part of f. One of 3 things happen, and I wanted to work through these 3 things with you, and then we'll look at some examples in the next video. So case 1 is described as f has a removable singularity at z0. And what does that mean? Okay, so that happens if each coefficient b sub n is just 0. And this is for all n greater than or equal to 1. So what I'm saying, practically speaking, is you have a removable singularity if all the coefficients of the negative powers of z are zeros. So in essence, there are no negative powers of z. It's just the constant a0 plus all the positive powers of z. In that case, we're going to say f has a removable singularity at z0. And so I want to point out to you that this is a nice thing. And so let's just make a little note here. Maybe I'll switch colors. Let's use something nicer. Let's use pink. So in this case, we can define or maybe redefine, depending on the function, I don't know. We can define or redefine f at z0, and then we're going to do that, let's say, such that f of z0, now let's go scroll up. This part's gone. It's all 0. And when I look at this series here, this is going to look like a0 plus a1 z minus z0 to the n, so on and so forth. When you plug in z0, you kill off all the powers of z minus z0, and you're left with only the constant, because the constant you can think about as a0 times z minus z0 to the 0. So that's what you're left with. And so the point is, when you plug in z0, you expect to get out a0. So we can either define f at z0 as a0 or redefine depending. And so thus, in that case, when you look at f of z, which we just saw, we can write as the sum n equals 0 to infinity, a sub n z minus z0 to the n. So in other words, the Lorentz series for f is just its Taylor series. Okay, and in that case, you now know that this expansion is valid at z0. So it's valid on not just the deleted disk z minus z0, but the full disk z minus z0 less than r. So you don't have to delete z0 anymore. And so the name is very suggestive, right? You can remove the singularity there by defining f at z0 in the right way. And it's the obvious way if you're looking at the Lorentz series. All right, so that's case 1. Case 2 is a little bit less glamorous. So f has an essential singularity at z naught if there exist infinitely many coefficients b sub n that are not 0. So there might be lots of them that are 0, but there's infinitely many coefficients that are not 0. So in other words, you've got infinitely many negative powers of z minus z naught showing up here in this sum. So that's an essential singularity. All right, so you have a removable singularity, which you can get rid of, an essential singularity, which basically means there's not much you can do. And finally, the third case is the interesting one, really. It's the case that we're going to care about the most in some ways. Z has a pole of order m at z naught, and make sure that we're comfortable with the language here. So a pole of order m at z naught if only a finite number of the b sub n are non-zero. So almost all of them are 0. Only finitely many are non-zero. Now, what does the m come into the game? I should tell you about the m. So let's think about it. So in this case, if only finitely many of them are 0, then there's a maximal m that's not 0. So in this case, there exists an m greater than or equal to 1 such that b sub m is not 0, but if you go up, b sub n plus 1, that's equal to b sub n plus 2, plus all the other ones are 0. And so just to be very, very clear here, so i.e., in this case, you can write your f of z as the positive powers part, a sub n, z minus z naught to the n, plus, okay, you've got some b1 over z minus z naught, plus some b2 over z minus z naught, and then you keep going all the way out to b sub n over z minus z, oops, sorry, this should be a squared. b2 is over z minus z naught squared, and then bm is z minus z naught to the n. And that's it. All the rest of them are zeros. Now, I want to point out to you, the only coefficient that I'm insisting that's not 0 is b sub m, right? So this guy can't be 0 if you're a pole of order m. Maybe this one and this one and this one are all 0. That's fun. That's fun. But you're a pole of order m if the coefficient on the mth power of z minus z naught downstairs is not 0. And then, by the way, we should make just a little remark. Let's find a nice color to write in. How about that one? So let's just point out that poles of order 1 are called simple poles. Poles of order 1 are called simple poles. So let's stop this video here, and then in the next video we'll look at some examples of this.